demo time. So I told you I would do some demos, and I'm going to try my best so that you can see everything. But everything's not very visible. Let's just start off with, this is my favorite one. This is really just a coil of wire, and it has an iron core right here. So it's a coil of wire, and I have it plugged into the outlet right here. It's turned off right now, which is not a great idea, but I did it anyway. It was designed back when that was okay. Now, so what happens when I turn on the outlet right here? Well, this is plugged into an AC circuit, so I get alternating current. Current coming in, current coming out, current coming in, current coming out. And so that's going to make a magnetic field. The current makes a magnetic field. The changing current makes a changing magnetic field. So remember, we calculate flux, magnetic field, area, cosine, the angle between the two, and the EMF is produced with a changing flux. So if I change the flux, I can produce an EMF. Let's see the first example of that. So here I have a coil of wire, and it's a Christmas light right there. So I'm just going to put that on top. It's not touching anything, right? It's just sitting there. And let's look at that light bulb when I turn on the coil. So you can see that it's not even touching. Oh, that's attracted. It's not even touching. And it lights up. So this is an example of the changing magnetic field due to this producing an EMF in the loop, and that EMF, since it's a closed circuit, produces a current, and that current lights the bulb. Boom, wireless power. This is how your wireless phone charger works. Same idea. But you'll notice that as I get really far away, the magnetic field decreases, and I don't get any change in flux enough to get a big enough EMF, and it doesn't work. So you have to get it really close. Now this thing, this is an aluminum ring, which is not magnetic. It's not ferromagnetic. When I put this on here and I turn it on, we can see something happen that's kind of fun. I caught it. So it's called a ring launcher. What happens is that the changing magnetic field here produces a changing magnetic flux in the loop. That changing flux induces an EMF around the loop. That EMF around the loop produces a current. That current produces a magnetic field. And because of Lenz's law, the direction of the magnetic field produced by this opposes the change in flux right there. So essentially they repel, so it gets shot up. Ring launcher, that's pretty cool. Okay, let's put that down and let's move on. I'm going to move this over here. Oh, it's kind of heavy. Now I'm going to go in no particular order. I have these things up here. If I can get it out. So I already showed you this, right? This is a coil of wire. If I move a magnet in and out of it, I can produce a current. So we don't need that. Let's instead, let me just start with this. I'm not going to show you a demo because it's a sound-based demo, but you probably know what this is. It's a speaker, right? So a speaker works by connecting wire. This is this kind of speaker. There's more than one kind of speaker. A wire comes in here and it produces a current, and inside there's a coil of wire. That coil of wire makes a magnetic field, and there's a magnet in there. You can see it sticks to stuff, and that makes it attract, and that pushes this cone back and forth really fast, and that's how we can make music. But that's not the demo I want to show you. If you take this and you plug it in as a microphone, this is also a microphone. So what happens is when I speak to it like this, the sound I produce pushes this cone back and forth. That moves the coil closer and further from the magnet, and that changes the magnetic flux, which makes an EMF and produces a current. So I can record that current in some way by speaking into it. So a speaker and a microphone, this kind, are the same thing. It's not the best microphone, but it is indeed a microphone. There are lots of different ways to make microphones. It's kind of cool to talk about them, but that's another day. Where are we at now? Okay. Let's look at this. This one's pretty good. I think I need to move the camera. Oops, what if I just move this closer? No? Okay, I'm going to move the camera, but I'm afraid I'm going to lose my connection, and it's going to make me very mad. Let's see. I'm just going to hold it. Don't touch the camera. Okay. So this is a coil of wire, and here's another coil of wire. So if I put this coil in there, if I change the magnetic flux, the magnetic field due to the inner coil, that'll have a change in magnetic flux on the outer coil. Now you'll notice that this one has few turns per length, and that one has much finer turns per length. So they have different number of turns per unit length. And this is a transformer, right? So I can apply a voltage here to the inner coil, and that will produce a voltage there. And based on the number of turns, the ratio of turns, the changing voltage here will give a different changing voltage there. So let's just plug this in and see if it works. I'm going to plug in my galvanometer. I really want to move the camera. I'm going to move the camera, right? I mean, you got to take some risks in life, and this is one of them. So please don't mess up. And now I'm going to move it a little bit closer. Okay, down a little bit more. That's good. Okay, good enough. Okay, so here I have the coil of wire. I'm going to take this one and connect it to a battery, and we can see that when there's a changing current here, then there will be a changing, I'll get an induced current here. And I'm not going to have, I could take this and hook it up to an AC source and you can see much more, but it's just a little more complicated. So when I turn this on, and notice that once the current is stable, the non-changing current, this goes back to zero. I only have a current in here when the current in here is changing. So you can only use this for an AC source. Okay, let's look at something else. I really like this one. Let me just plug it in and then we'll see what happens. So I'm going to connect this right here. Connect this one right here. And I'm going to take my battery and then my battery right here. So this is a buzzer, okay? I mean, that's not that great, but there's something awesome about it. So the idea here is that these are electromagnets, right? When I run electric current through these electromagnets, then it's going to pull a little metal piece in here down. And when that happens, it disconnects the electromagnet and it turns off the electromagnet. And then when the electromagnet's off, the spring pushes it back up, so it turns back on. On, off, on, off, on, off, on, off, on, off. That's not the cool part. The cool part is that since these are inductors, they have inductance and they produce a change in voltage when there is a change in current. So when the current turns off, then they will produce a very large voltage. And this can actually produce tiny sparks in the contact down here, because the voltage gets high enough to break down the electric field of air and you get a spark. And the cool thing is, I know I keep saying cool stuff, but the better part is that those sparks produce electromagnetic radiation, which we'll look at later. And this is your most simplest basic radio transmitter. This is called a spark gap generator. So you can actually, if you put an AM radio near this, and every time you turn it on, you'll hear the radio go bang too, okay? And this is a radio. You don't have a frequency to change. It's all frequencies, okay? But it is a radio. These are the earliest broadcast radios, and that's pretty cool. Let's get this over here. I talked about hand crank generators before, so here's a hand crank generator, and I showed you this. Let's just turn this. I feel like my lighting, okay, but this is just a motor, and if I take a battery and connect it, I'm just going to hold it there and connect this. So you can see that a generator and an electric motor can be the same thing. They're not always the same thing, but they can indeed be the same thing. Okay, so those are the main ones I wanted to show you. I think I'm just going to stop there. Yeah, the end. Okay, that's it.